Hi, this week we look at dynamic programming tasks. It's the first week of dynamic programming tasks. We will look at a simpler one. The problem are pretty much one-dimensional, with exception with some simpler problems. Okay, um, you need to basically review what you learned from class first, and then we will see how to work out the problem set. Okay, um, the idea of dynamic programming, let me review that really quickly. Okay, so the idea is that you have a task that you want to solve. Okay, that you want to solve, and basically this task can be solved in many ways. There are choices that you have to make. Okay, but um, that you need to make, but this choice give you you want to make some choice. Okay, um, but for each of the choice that you make, um, you it give you a few subtasks. What I mean by subtasks is like um, okay, you make some choice, and then and then given the choice that you have made, um, uh, there's some problem that you still have to solve, right? But pretty much all these subtasks are the same as the original task, but they got smaller. They have fewer input, stuff like that. They usually are smaller. Okay, in some sense. Okay, so you can basically use the same idea to solve the task. So you solve this recursively. Okay, however, the number of subtasks that you have are not too many, so you can basically so typically you cannot do this in general, because um, after you made some choice, there are a lot of subtasks, and then the number of subtasks go exponentially. So you cannot use this idea. But in dynamic programming, pretty much the number of subtasks are quite small, so you can recursively solve them, and keep do some bookkeeping, right? Okay, so that's pretty much the idea. But we'll look at concrete problem first. Okay, so let's look at the task that we have to solve. So let's look at stair first. Okay, you should go ahead and read the task statement for a bit, and then we'll come back to work on the problem. Okay, so in this task you have a stair and steps, and you want the count the number of ways you can climb up, but you can skip some steps. So they basically so let's look at you can skip at most k step. Okay, so let's look at some examples. So let's say k equals 2, which means you can climb one step or two steps. Okay, so if you have when n equals 2, you can do this one step. Okay, or you can do this. So there are two ways. When n equals 3, you can do this, you can do this, and you can do this. So there are three ways. Okay, you can try to when you have a problem like this, you can try to understand the problem by looking at examples, but this won't give you too much of the insight, but it gives you some understanding, right? This is the first way you do it, or maybe you do that. Okay, maybe you do that. That's the third way. Maybe you do that. Okay, maybe you do this. Okay, in many ways, so you can count, I think. However, to come up with a solution to this problem, you need to try to you need to deal with general case with n, right? So that's not easy. You cannot try to do 2, 3, 4, 5, 6 and understand that, right? So let's look at the small steps. Okay, There are many ways to look at that. So one way you can look at that is like you have n steps. Okay. Um, okay. How can you reach this the last step? Okay. You can ask the question like that. Okay. You can do it in two ways, right? You can go from the n minus one step or n minus two steps. Okay. So from here, we can express the number where you can climb up the stair recursively. The other way you can do that is like you look at the bottom one. Okay. So you have two choices, right? Either do this or do that when k equals 2. If you do this, then the rest of the stair steps that you need to climb is n minus 1. If you do this, the rest of stair you need to climb is n minus 2, right? There are two choices. Okay. So it's the same kind of thing here. If you jump from here, then this is like n minus you have to go to the n minus 2 step first. If you need to go here, need to go to n minus 1 step first. Okay. With this, we can express the number, the same idea. It's gonna give you the solution. So if we let ai be the number of ways to climb stairs. Okay, you can express the case, the basic case like this. You can say if you have want to climb n steps, it would be okay. So you should pause the video for a little bit and try to come up with the recurrence. N should depend on something that are smaller than n. Okay, and then we will try to come up with the solution. Okay, so you should pause the video and try to think about the recurrence. Okay, I hope you think about the recurrence already. So basically, you can look at this. Okay, so there are two ways, right? The first way is like you take one step from the step n minus 1. So that the first choice, take one step from the n minus 1. The other choice to take 2 steps from n minus 2. Right? But if you take the first choice, how many ways can you do it? And if you take the second choice, how many ways can you climb the stair? So you know that recursively, if you take one step from n minus 1, there are n minus 1 ways to do that. And from n minus 2, there are n minus 2 ways to do that. So you have this recurrence. Okay, this is called recurrence. Okay, so with this we can pretty much solve the problem when n equals 2. However, if you recall, when you define a recurrence, you need a way to deal with the boundary case. So basically, if you have a0, if you have no stair at all, right, then there's one way to do it. It's like you don't climb any stair. Okay, now if you have one step, okay, that's just one way, right? So you have something like this. Okay, and then the rest should just follows. Okay, so if you look at this, you have a n and you need a n minus 1 and n minus 2 previous values. So this is the boundary condition. And in general case, when k is larger than 1, then you need to somehow think about the case in the other way, but you cannot just try them all. Okay, all right, so this is the recurrence. But if you write a program like this, so given this, you can write a recursive solution. This is the key first step, come up with the recurrence. This gives you a recursive solution. So let's write function num. Let me write in Python. Okay, so let's write let's actually write some code. Okay, So let's write function num steps num let's say num clam. Okay, let's do that. Okay, this function numClam is just the recurrent that we wrote before. So if you look here, it's n because we want to climb in steps, right? So, and let's make it work just for k equals 2. Okay, so if I equals less than equal to 1, right? So return 1, else return numClam n minus 1 plus numClam n minus 2. Okay, this would be a really big numbers, but we'll deal with that later. Okay, so so let's run it. Oh, oh, okay. What's wrong? Oh, okay. So okay, this is wrong. Okay, should be I, right? Oh, okay. Then I have infinite too many recursion levels. Okay, so let's see. Okay, 5 and 2. Okay, 3, 4 and 2. 5 ways. So this is like exactly like what we try. Okay, like 3. This is 3 ways, and if you have 4, then it's 5 ways. Okay. All right. However, if you have really large input, so let's say 10 to take some time, right? But then 102, it would take forever. Okay, so okay, there are a few things that we have to fix here. First is the number of steps can be really large. Let's see, like it's get pretty large. Well, it can get really large. It will be larger than an int. Okay, but if you look at the task statement, it says you need to do this modulo 9377. So let's do that first. Okay, so after you add stuff, you just do this, and then we mod. Let's make a so it's a good practice to create a constant like that, because then if you wrongly type it, then you can fix it in just one place. Okay, so this is the first step, but then it takes so long, right, to run this code when n is large, and this like n is 1,000, then you have no way to complete it, okay, on time. Okay, so we halfway through the idea of the dynamic programming. So the recursive solution can be really slow, because if you try to call like a10, let's see, it will recurse on a9 and a8, right? And a9 would call a7, and a8 would call a7. If you do that recursively, right, and so on, and a5 would call a4, a7 would a8 would call a7, and a6. There'll be a lot of duplication here, right? So you can save time by remember the solution through the recursion like this. You can have a table that basically keep you the solution instead of making recursion every time. So we do this. So we have a table. Let's call it A. Okay, and let's say the max n is stuff like that. let's say cons in max and min. Okay, and then initially we need to initialize a, so that if a is we know that sum of the slot is not computed, we need to compute it, and then if the next time we see the value, then we can just use the value. So this is what I'm gonna do. So I'm gonna initialize the value of a to be -1. In that case, I know that I don't know the value of the result. Okay, so here let me do some optimization. So if a I is not -1, then I just return ai. Otherwise, I need to compute it. So I say ai. This is the same code previously, right? So and then I just return. Okay. Okay. You can write it a little bit better like this. If I haven't computed the value, then I compute it and then I return AI. Okay. Okay. So after this, let's say it's really fast now. Okay. And you see that the value is really small, but it's small because we do the mod here. Okay. All right. So let's try to submit it. It won't give you full score because the task asks you for k equals 1, 2, 3, and 4, right? But anyway, let's try to submit it. Okay, so it gives you 40 because yeah, it works for k equals 2 only. All right, so this is the first way to implement dynamic programming algorithms. It's called memoization because you actually take the recursive function and then try to optimize it through this memoization. Okay, but for many problems, you can just write down the calculation right away, right? Without having to do the memorizations. So you look at this task, right? So if you look at this top down, okay, you can see that you want to compute an, and then to compute an, you need to compute an minus 1 and n minus 2 and so on. But if you do that bottom up, okay, so let's look at this. This is like the way you do it top down, right? But you can see that if you want to compute A10 and you have A9, A8 already, then you can just add them up, right? It will be really quick. So instead of doing top down and having having to save the previous value, we work it bottom up. So the idea is like we start with something that we know. Let's say A0 equals 1, A1 equals 1. And then we build on that. So we'll just do the for loop up to n. And then we know that we want to compute AI, right? But at the time we compute AI, we already have the previous value of A at our disposal. So I can just write a code like this. And then mod m like that. So the code will be really simple, just like this. Okay, so let's try to fix the code. So you can just throw away this. Okay, so let's see. Okay, and then I can also ignore the initialization. I can just say A0 equals 1, A1 equals 1, then and then I'll write the computation here, and then I just print out the an here. I can say just AI equals AI minus 1 plus AI minus 2, then do the mod. Okay, so that's the code. It's really simple. Okay, but if you understand it, it's simple. If you don't, it's like completely magic. Okay, so let's try to submit it. Okay, same score. Okay, all right. So this is the typical way that you see people write dynamic programming code. It's the next step. If you look at the steps in, if you look at step in solving the dynamic programming that we mentioned previously, to keep the result in table, you can do it two way. You can do it top down by just following the recursion function and optimize it. You can do it bottom up. Okay, two ways. This is the way people usually work on, because people would do this, come up with the recurrence and get the boundary condition, and then they won't write a recursive function. They work bottom up and then write iterative version. Okay, so this is what people usually do, and then you have a simple loop for solving the task. Okay, right. For the other value of k, you need to try to do that on yourself. But the key difference is like it's in the base case. Okay, so when you have k equals 3, k equals 4, then the recurrent will change a little bit. Okay, but it will depend on more values. So your boundary condition need to be you need to handle the boundary conditions. There are basically two ways to do that. You can hard code it, or you can do the same thing. Okay, so you can just have this one boundary condition, and then when you compute the value, you think about if you go like you want to go to if k equals 4, let's see that, and you want to do the case when you at the second step, how many you can do that. So recursively you say you can climb up to this from 1, right? You can do this from 0. You can do this. This is the ground, right? So this is your ground. This is ground. But the recurrent would say something like that you can climb up to this point from underground, right? Which is not possible, right? So you need to ignore these possibilities, right? Because this is the ground. This is ground zero. Okay, so you can do that in your recurrence. When you want to compute recurrence, you add some condition to it, then you should be fine. Okay, so I'm gonna leave this task for now, and then let's look at another one.